Hello again. So today we're going to start asking the question, how do we improve on the humble forward Euler scheme, both in terms of accuracy on the one hand and stability on the other? And we're going to start by looking at implicit schemes which aim to improve the stability properties of the forward Euler schemes, sometimes also called backward Euler. And this question of how we improve on forward Euler will sort of thread us through the remainder of ordinary differential equations methods in this lecture, in this module. Okay, so I'll hand over to the board again. Bye. So last time we left off with this question is, how do we improve on forward Euler? And remember, forward Euler worked quite well for the exponential decay case, but it didn't for which was stable under some cases for exponential decay, but not for and this is a huge weakness really, because if you think about any sort of real examples, if you have some phenomenon that's, say, describing population, say, and it's oscillating and it's decaying, if you can only capture the decaying part of that problem and not the oscillation part without instability, then we're in trouble. So what we're going to do is go through the different methods of methods. So first of all, we're going to look at what's called implicit schemes. And this tends to wants to improve on the stability aspect of the forward Euler. And it's sometimes for that reason called backward Euler, and explain what I mean by that. So let's just go back to our fundamental equation we're solving. We're solving dx by dt is some function, and in general it's of x and t, but we're just going to consider it as a function of x, okay, for this reason. Just prove that. And if we do the forward Euler discretization, then your x's go to xn, so this becomes xn plus 1 minus xn on delta t. And that's our first order discretization of dx by dt. And the right hand side then, believe it or not, is just simply f evaluated as fn. And that's a subtle difference. That's why sometimes it's called backward Euler or implicit. It's all about changing this term on the right hand side. So sometimes forward Euler is called explicit. And the reason being is that you can rearrange your forward Euler in terms of an explicit expression for xn plus 1 in terms of previous time steps. Okay. Whereas an implicit scheme, you can't do that, but it has better stability, and I'll show you why. So the big subtle change is almost, if you don't focus on it, you'd miss it, is we then, instead of having xn on the right hand side, we have xm plus 1. So So that's a big change. And now it's hard, not in general, it's harder to write an explicit expression of n+1 in terms of previous steps. You have to do a bit more algebra. But my contention, the reason you do this is this improves the stability. Okay, so going from forward order to backward order, we're going to improve the stability. And we're going to do our stability analysis again with this case. Okay, so that's the idea. Let me just write a little bit more on what explicit and implicit is. I try and write as much as I can on the board rather than just say it. So you know you've got as full a record of things as possible. So explicit means xn+1 is in terms of everything evaluated on previous time steps, n, e.g. n, e.g. n. Okay, so that's the explicit one. Implicit is when this isn't the case, so we've now evaluated the right hand side at case. So e.g. this change of f of x and n to f of x of n+1 now. Okay, but has, and I need to show you this, better stability. So there's often a trade-off somewhere. Often with implicit schemes we have to do more algebra, maybe more computation, but the gain is gold because you've got stability. With some explicit schemes, they're intrinsically unstable, as we saw for the forward Euler. If you've got instability, as I say, there's nothing you can do about anything else. So those are the sort of two paradigms. So actually, with much more complex numerical systems than we're looking at in, say, real-world examples, say where you're modelling the weather and climate, at the Met Office, where you're modelling the flow around a Formula One car at a Formula One team, we're trying to model river flow. It goes on and on, the examples, really complex schemes. Often the question that people ask is, how can I make my schemes as implicit as possible? How can I make them as stable as possible? Because then they're going to work, then they're going to give robust results, and they're going to give results that we can believe. So this is a really, these words are actually very important in real world, should we say, applications of numerics. Okay, so let's look at some examples. So let's return to our friend exponential decay. And remember, so here x is real. Remember, lambda is greater than 0, etc., etc. And now we're going to do a implicit or backward order discretization. So the key thing we're going to revise before we evaluated this at step n, now we're going to evaluate it at step n+1. So the left hand side is simply xn+1 minus xn on delta t. I hope by this stage you're using delta t and you've given up this notation of h, because delta t tells you a lot more about what you're doing. It tells you to discretizing in time, okay, and then you're using this notation. Mathematicians get quite hot and bothered sometimes about notation, but these things I think are quite important in the subject of numerical methods is using it like this. So because it's sort of it's a clearer statement, it shows you know what you're doing a bit more. And then it's minus lambda x m plus 1. Okay, so the key thing is this m plus 1 here. So if we now rearrange this, do just a little bit of manipulation, we get xn plus 1 equals xn minus lambda delta t xn plus 1. Now this is an implicit method that actually is algebraically quite simple as well. But in general, if you have a right-hand side that is a more complicated function, or certainly if it's a non-linear function, then this rearrangement is not so simple, and that's where all the extra computation comes in. We're sticking with our simple examples, trying to understand how it works at the moment. And then we want to get xn plus 1 onto one side. So maybe an extra line of algebra now in the implicit method is in getting n plus 1s onto one side and n's on the other. Okay, but it's still an implicit scheme in the way it's written down. So one more step, 1 plus lambda delta t. Should applies our amplification factor. A is amplification. And remember, with the exponential decay case, so it's real, we don't have to worry about complex numbers, is xn plus 1 divided by xn, which is 1 plus 1 plus lambda delta t. So let me just write that down. A is 1 plus lambda t delta t is implicit. The implicit method, stable. Remember, lambda is positive constant, delta t is always greater than 0. Just pause a little bit, so I'm gapping things a little bit at the moment, just to give yourself time to think about the material rather than just passively absorb it. Okay, let me just improve that. Okay, so I'll just pause for a minute and then you can come back to it. So the answer is, well, A is less than 1 for all delta t. Lambda is greater than 0, so that A is less than 0. So it means that, and the true solution decays. So that means the numerical solution is going to decrease so the numerical solution decreases with each step, as does the true one. So yes, tick, it's stable. But the even better way is it doesn't depend on, it's unconditional. Yeah, so A, which is 1 plus lambda delta t, A is less than 1 for any delta t. So that's different from the forward Euler case, which was only stable for some delta t. So it's unconditionally stable. Whilst, recall, forward Euler, Fe, was conditionally stable, dependent on the delta t. Okay, so you have unconditionally stable. Any delta t and A is less than 1, it always decay. So just remind ourselves, the diagram is always very useful. We have the true solution here. The numerical one, it might not be completely accurate, but it's always going to decay. So even with this simple example, we can see that the implicit method is always stable. It's unconditionally stable. Okay. If we just going to keep track of the time. Yep, I've got a little bit of time to do this. So what we've done there is we've improved the accuracy of, the stability of the scheme. Implicit, the implicit method improves on the accuracy, stability of the forward Euler method. I'm just going to introduce you to another method that tries to have the cake and eat it. It tries, what about also improving the accuracy? From first order. Remember the right hand side approximation for forward Euler. Forward Euler has dx by dt is xn plus 1 minus xn on delta t plus order delta t, and that order is your first order accuracy. How can we improve on that? Well, I'm just going to really just state one. This theme will come up again and again with other methods, but there's one common method out there. There's this so-called trapezoidal implicit method. I'm just going to write it down, okay, because we're going to come back to it. And that is, we have the same left-hand side, but instead of just having f of x of n, we do an average, essentially, okay, like finding the area of a trapezium, hence the trapezoidal nomenclature. We do an average, so we average step n and n plus 1. So it's called trapezoidal implicit, or sometimes it's also named after the people who came up with it, Crank and Nicholson. This is a thing you'll find about sort of numerical methods, or optimization methods as we look at them. Some will have people's names on them, with obvious reasons. They were the first to discover it, but it doesn't really tell us what it's about. Others will tell us what it's about. So trapezoidal implicit tells us a lot more than Crank Nicholson doesn't, but they're basically the same scheme. So that's just a little comment on his sort of history of how of numerical methods. So the idea is, what we do is we try and get some more accuracy by, instead of having f of xn plus 1 and xn plus 1, so it's kind of a mix of an explicit scheme and implicit scheme. And we'll see later that this is second order accurate. And we're going to look at this method. It's right at the end of this section of module. It's the Adams-Moulton method. Okay, so bear that in mind as we come forward. But I just want to show you where you can go forward, where you try and have accuracy and stability. So you have some element of implicitness with the xn plus 1 and the second order accuracy. Okay, so that's our first step in improving on forward order, is implicitness. It's an absolutely central concept in numerical methods. So just transforming the right hand side from step n to n plus 1 gives us better stability, and we've shown that for the exponentially decaying case. Okay. And I'm going to stop there now.